Hi, welcome to this class. This class is divided into 2 or 3 modules, we will see, and we are focusing on silicon dioxide and photolithography. Now, if you understand photolithography is a heart of any micro fabrication or micro engineering process. So, it is very important to learn and understand how we can perform photolithography. Okay? But before we understand photolithography, most of the substrates, most of the devices in semiconductor area or arena is made out of semiconductor, right, and that semiconductor is nothing but silicon. So, we should first understand how we can get a silicon wafer, right, because that is the substrate that we will be using. Now, when we talk about substrate, what exactly a substrate means? Substrate means any material on which you are going to fabricate a device. Now, whether it can be whether it is a metal or a semiconductor or insulator, it does not matter. The base that we are using to construct the device, the base is called a substrate. Now, if you have seen generally MOSFETs or transistors, right, MOSFET is also a transistor, BJTs or even some accelerometers, some sensors, pressure sensors, right, they are all fabricated on what? On silicon. So, when we talk about silicon, how silicon wafer looks like, right. So, I have a silicon wafer in my hand, you can see here this is a silicon wafer. Now, you see here, right, this is a rough surface. How can you see it is a rough surface? Because on another side you can see is a polished surface, right, you can see very clearly a polished material. There is some pattern on silicon wafer, that is you do not have to worry about it right now, but the point is you can see a silicon wafer right in my hand, right. Now, this silicon wafer, it is a 4-inch silicon wafer. So, let me hold it in a way it should be holded. First of all, you should not hold it with bare hands, you have to wear gloves, but this is just for demonstration, that is why I am holding with bare hand. As you can see, there is a flat surface here, you can see a flat, there is a one flat, there is a second flat. These flats are meant to understand whether it is p type or n type, or it is 100 or 111. We need to understand what kind of wafer it is and what is the orientation of the wafer. To understand this orientation and the wafer type, we are using the flats, right. So, flat can be at 90 degree as shown in this wafer, it can be at 180 degree, it can be at 45 degree, or it can be only one single flat. Now, the big flat that you can see here where my thumb is, you can see here, right, this is a big flat, while there is a small flat right over here. This is a small flat, this is a big flat. So, primary flat and secondary flat, we say like this, okay, primary flat and secondary flat. Primary flat is bigger, secondary flat is smaller. Now, in some wafer you will only find primary flat. Again, like I said, to distinguish the type of wafer and its orientation, we have the flats placed into the wafer. Now, but the question is, how can you fabricate this wafer? Why it is called wafer? You can see it is thin in size, right, it is extremely thin. Now, it can be 100 microns, it can be 200 microns, 300 microns in thickness. This is a 4-inch wafer, the one that I am holding right now is a 4-inch wafer, 4-inch wafer with a thickness about 400 to 500 microns, alright. So, this is the wafer. So, now you can see here there is a rough surface and there is a polished surface. So, again when you talk about wafers, they are polished wafer or unpolished wafer. Now, if it is one side polished is one side polished, it is called single side polished wafer. If the polishing is done on both side, it is called double side polished wafer. Now, depending on the diameter of the wafer, this is a 4-inch wafer like I said earlier, and the diameter of the wafer, the thickness varies. So, for this wafer that I am holding, the thickness is about 500 microns, 500 plus minus 50, that is what it is written in the specification, 500 plus minus 50 microns in thickness. So, this is the 4-inch wafer. Now, substrate, when we talk about substrate can be a glass also. So, this is a glass substrate, you can see here, again I am holding in my hand, right, a glass substrate, right. So, you can clearly see is a glass, right, on which again there is a pattern, some pattern is there on the glass. This is again a wafer, and it is a 4-inch wafer, about 100 microns thick, right. So, this glass can also be used to fabricate device. You can see some pattern on this glass, this is nothing but a heater, heater we have pattern on this glass, and we will discuss about these things, how you can pattern different materials or different components or different devices on different substrates in a later section of the this particular course. The idea right now is to understand what are the kind of substrate, in particular silicon. So, this is another type of substrate. Now, let me show you one more type of substrate, and this substrate is using a plastic. So, I am holding another substrate in my hand. This is using plastic, okay, the bare plastic. So, you can fabricate a device on something which is similar to a plastic, right. So, plastic can be a substrate, again there is some pattern on this plastic, right. So, plastic can be a substrate, a silicon can be a substrate, a glass can be a substrate, right. Now, the question here that we need to understand, or the point here that we need to understand is how we can get this silicon wafer, because silicon 70% or more than 70% of the devices today available around us, the base is silicon. So, when we talk about silicon, how we can get this silicon from the raw material, alright. That is the idea to understand in today's module. So, when we talk about silicon, let us see on the screen, right, let us see on the screen silicon. So, silicon bowls and wafers, right, we have seen just a wafer right now, right, 4-inch wafer, and this wafer occurs from the bowls which are large logs of uniform silicon, right, like this. Now, looking at this picture, where do you think silicon bowls are made, and why do you think so? That is a question. So, of course, we can see that it is made, the silicon bowls are made in clean room, So, when we talk about clean rooms are classified into several class, and we in this particular course we will see class 10,000. Clean room facility. I will actually show you how the class 10,000 clean room facility looks like, right. I will take you to my lab, of course through videos, and you happen to be in IISc in one fine day, and you want to visit my laboratory, you are welcome to do so. So, class 10,000 clean room facility, okay. So, how it will look like. Now, this is what we will be looking at, but when we look at the silicon, this is even at a lower class, that is a better environment. It can be at class 10, it can be at class 100, and it can be a class 1000. So, we will see what are the class and what are the clean room classes, how clean room is classified. Now, why we think that this is a clean room, right? First thing we answered, where do you think silicon bowls are made? We think that they are made in a foundry under clean room, which has a clean room facility, right. So, first we have answered. Why do you think so? Why we require clean room? What is the answer? The answer is to avoid contamination, right. We need a silicon which is 99.12345678 and 9 times 9 pure. So, to obtain this we require a clean room facility, and this clean room facility is a place to avoid any contamination. So, now we know that if a bowl is there, if you have a bowl, then we can slice the bowl and we can get the silicon wafer. Of course, there is a process, we will see the process also. So, this is what we want, right, this is what we want, and how it is made. So, the initially melting of polysilicon. The polysilicon is melted, right, by at very high temperature, and you can see in this particular figure that there is a crucible, right, there is a crucible, there is a crucible shaft which helps the crucible to rotate. Then we add the silicon polysilicon crystals. So, there is a silicon melt, here there is a crucible, here the crucible susceptor is there, there is a heater surrounding the crucible, and then there is a thermal shield, right. Now, we dip a seed holder with a seed crystal, like this, a seed holder with a seed crystal inside this hot molten polysilicon. Now, when it is dipped, right, and when it is pulled back with rotation, then it starts forming a single crystal, right. Seed crystal is a single crystal where you dip the seed crystal into the molten polysilicon and you start pulling off with a rotation, and the crystal starts growing. So, this is a beginning stage of the crystal. Now, when you start pulling the crystal, it starts forming the single crystal silicon, and at the end you will be able to see the bowl that we were looking at in the last slide. So, this is how the bowl is made. You can see from here a molten silicon, the seed crystal is inserted, you can see here it is inserted, and now it is pulled back, right, and once it is pulled back you can form a single crystal silicon rod or a bowl. Okay. Now, one thing that you need to understand is that both the shaft and the seed crystal both moves in a opposite direction, both moves in a opposite or anti-clockwise. One is clockwise, second one is anti-clockwise direction. So, once you have this single crystal ingot, it is also called ingot or bowl, then what you will do? First is you have to grind and trim the crystal, you have to remove the edges, right. So, this you see here we have trimmed the edges. Next, what is the process? Next process is you have to perform a flat grinding. Why you want to perform flat grinding? So, that we can get the primary flat. We have just seen, right, how primary flat looks like. So, to get primary flat we had to do a flat grinding. After flat grinding we have to perform wafer slicing, right, wafer slicing. Wafer slicing is done using a diamond thread. Now, after wafer is slide you have to perform edge rounding, right, you have to round the edge. Then there is a process called lapping, followed by chemical etching, followed by polishing, right, lapping, wafer etching, followed by polishing. Wafer etching is to get smooth wafer. There is a extremely smooth wafer with nanometer finish, surface finish. Now, once you have this, what is the next step? After this you have to polish it. Once you polish, next step is to inspect the wafer, right. So, starting from a crystal growth, that you are loading polysilicon into the hot crucible, and then this hot crucible polysilicon is in melted form, and then you dip the single crystal and you rotate it and you pull it off and you get single crystal ingot, right, followed by crystal trimming and then diameter grinding, followed by a flat grinding, followed by wafer slicing, then edge rounding, lapping, etching, polishing, and finally wafer inspection. This is the process that is followed to obtain finally the wafer that we have seen at the starting of this class. This is adapted from 2005 VLSI Tech. Now, this is how it will look like. This is how it will look like. So, you have these bowls, you can see here, right, this bowl, and when you do the edge, you remove the edge by grinding, you can just or trim the edge, then you have this one, right, and then like I said, diamond coated wire is used to slice the wafers from the ingot. After slicing, you can use the lapping machine. You can see here a lapping machine to lap the wafer. After lapping, there is a chemical wedge and then polishing, finally the inspection. So, this is a video that you need to see, so you understand how exactly the silicon is fabricated, and just look at this video, and then we will follow the lecture after this particular video. Now, once you know that you have the silicon wafer, right, once you have the silicon, let us say, what is the next step? Next step is, you can, if this is silicon and if I start depositing a material on this silicon wafer, let us say if I deposit a metal, then what happens? Silicon is a semiconductor, metal is a conductor. So, we may not be able to get what we want, right, because it will be a short, between a conductor and a semiconductor. So, how to use silicon as a substrate? So, to use silicon as a substrate, we have to grow a oxide layer. So, let me draw so that we can understand. Okay. So, silicon, we have to grow oxide layer onto silicon, so that we can use silicon as a substrate. This is silicon, this is SiO2, this is SiO2. This particular wafer is called oxidized silicon wafer, oxidized silicon wafer. Okay. How you can grow this silicon dioxide? How you can grow silicon dioxide? That is what we have to understand today, and this silicon dioxide is nothing but an insulator, right. You can also grow silicon nitride. But silicon dioxide is heavily used in the IC industry, and that is why we need to see how silicon dioxide is grown, and second is what are the thicknesses of the oxide and that are used for different process. Okay. So, let us see. Now, why we have to grow silicon dioxide? Because if I take the same example, and if I deposit metal now, right, let us say metal looks like in this particular fashion. This is my metal, this is silicon dioxide, this is silicon, right. Then metal will not get shorted with silicon because of this insulating layer in between silicon and silicon oxide, correct. So, I have to use oxidized silicon wafer. Now, let us see. So, we have got different thickness of oxide. We have 1 micron oxide, we have 0.1 micron oxide, we have 10 nanometer oxide, we have 1 nanometer oxide. Okay. So, if it is 1 micron oxide, then it is used in filled oxides. So, if you guys know MOSFET, then you will understand a difference between gate oxide and filled oxide. Gate oxide and filled oxide. So, 1 micron is used for filled oxide, 0.1 micron is used for masking oxide. Where masking comes into picture? So, let us see. Let me draw here. If I want if I want to create a pit in silicon wafer, this is silicon, I want this structure. So, how can I obtain this structure? See, I know what are silicon etchants that can etch silicon, right. These etchants are KOH, potassium hydroxide, TMAH, tetramethyl ammonium hydroxide, and these etchants are used for different application. When I say different application is same, which is silicon etching, but are used at different temperatures. One KOH is generally used at 80 degrees centigrade, TMAH is used at 25 degrees centigrade, but when you etch silicon with KOH you get rougher surface, rough boundaries. When you etch with TMAH you get smooth boundaries. KOH is faster, TMAH is lower, right. So, these are the some differences in silicon etchant, KOH versus TMAH. So, the point is, if I want to create or if I want to etch silicon in this particular fashion from a silicon, from a given substrate of silicon, how can I etch it? One way is you protect silicon dioxide in this, you protect silicon with the help of silicon dioxide by patterning silicon dioxide in this fashion. Now, if you dip the wafer in KOH or TMAH, then sorry, then you will obtain this particular wafer. How and why? Because this silicon dioxide will act as a mask against silicon etchant. So, silicon etchant cannot etch silicon in this area, that is what we mean by masking oxides. All right. This is an example of masking oxide. Now, same way, changing the thickness of silicon, changing the thickness of silicon dioxide, we can also use silicon dioxide as pad oxides. We can also use silicon dioxide for gate oxides. You see gate oxide, see, we all know, right, that when we have MOSFET, we are just drawing a very simple diagram. Or let me just write down source, drain and gate, right. Source, gate, drain. This will be my oxide, right, which is extremely thin, right, close to 10 nanometer or even smaller, even the thickness is less depending on the MOSFET fabrication, and this is nothing but my gate oxide, gate oxide. So, again you can use gate oxide or ternary oxide depending on the thickness of silicon dioxide. Then we can also have chemical oxide from cleaning native oxides, right. From cleaning native oxides we can have chemical oxides. Now, deposited oxides can also be used on back end insulator materials between metal layers, and can also be used as masking oxide, right. Now, So, what is the etchant for silicon dioxide, right? We have seen etchant for silicon, that how can we etch silicon, but how can we etch silicon dioxide? So, silicon dioxide etchant is hydrofluoric acid HF. So, if you dip a wafer with silicon dioxide, this is our oxidized silicon wafer, right? Silicon SiO2, SiO2, HF dip, what you will get? You will get silicon, right. So, HF which is hydrofluoric acid, right, is the etchant for silicon dioxide. Okay. So, you have to remember whenever we use HF is for silicon dioxide. Now, in the common laboratory practice we use buffer hydrofluoric acid, instead of HF we use BHF for etching silicon dioxide. Okay, guys. So, you need to understand and remember that for etching silicon dioxide we are using buffer hydrofluoric acid in practical applications. Now, moving further, silicon dioxide can provide a selective mask against diffusion at a temperatures which are extremely high, right, because DE of SiO2 is extremely less than DE of silicon. So, when I dope silicon, right, why I have to dope silicon? For forming source and drain, right. If I want to form source and drain, I had to dope it, right, but if I dope it, I had to protect the remaining area. I had to protect the remaining area of silicon, so that the doping occurs only in the required region to create my source and drain, right. This doping when I perform, right, I am doping the entire wafer, but I am interested only in this particular 2 area. So, when I am doping, right, I can protect my area which are not required to be doped with the help of silicon dioxide. So, silicon dioxide can provide a mask against diffusion at high temperature. Okay. And what are the diffusion materials that are used for diffusion? Boron and phosphorus, depending on whether you want p type diffusion or you want n type diffusion, whether you want p type diffusion or you want n type diffusion, whether you want n channel MOSFET or p channel MOSFET, whether you want enhancement type MOSFET, whether you want the depletion type MOSFET, right. So, this is something is very important to understand, that the silicon dioxide application is not just limited for gate oxides or masking oxides or pad oxides, it can also be used for as a mask against common dopants. So, you can see here silicon dioxide mask boron and phosphor. Now, one way of doing is of course the diffusion technique to dope the wafer. Another way to dope the wafer is called ion implantation. Another technique for doping the wafer is ion implantation. So, silicon dioxide not only acts as a mask when we are diffusing the wafer, it acts as a mask when we are implanting the wafer, both ways, right. It is same thing, it just acts as a mask for against the common dopants. Now, we have 2 types of oxidation. One is called dry oxidation. In dry oxidation, we are reacting silicon with oxygen to form silicon dioxide, while in wet oxidation we are allowing the we are using the water, right, and reacting with silicon to form silicon dioxide plus 2H2, which is a gas. So, this is nothing but water vapor, is in gaseous form, water vapor. both typically. So, say dry oxidation as well as wet oxidation is carried out typically at 900 degree centigrade to 1200 degree centigrade. Another important point is wet oxidation is about 10 times faster than dry oxidation. Very important to understand, wet oxidation is about 10 times faster than dry oxidation. Now, dry oxidation forms a thin film of oxide from 0.05 to 0.5 micron, and the film that is grown, that is the silicon dioxide that is grown using dry oxidation, is an excellent insulator for gate oxides, and for very thin gate oxides we may need nitrogen to form oxynitrides. So, whenever you want to grow silicon dioxide for gate, we will be using dry oxidation. When you want to grow silicon dioxide for masking oxide, we will use wet oxidation. All right. So, wet oxide, if you see back on the screen, wet oxide, the thickness can be less than 2.5 microns. Again, it is a good insulator, not as good as the oxide grown using dry oxidation. It is good insulator for filled oxides or masking. The quality suffers due to the diffusion of hydrogen gas, because we are reacting silicon with 2H2O, that is vapor. So, there is a hydrogen gas which gas out of the film, creating the path that electron can follow, right. So, this is the drawback of wet oxide, that the quality suffers due to diffusion of the hydrogen gas out of the film, and that will ultimately create a path for electrons that electrons can follow. There is something which is always there. So, when you get a new silicon wafer and if you keep it at room temperature, there will be a thin layer of oxide, is a poor insulator, but can impede the silicon processing, and that is why whenever you get a whenever the wafer is in the room temperature in the laboratory, the first step that you need to do is you have to perform HF dip. That will remove your native oxide and get you the silicon substrate, right. This one, thin layer of silicon dioxide about 1 to 2 nanometer. Okay. So, another thing to understand about silicon dioxide, tricky, right, tricky, useful but tricky. Volume expansion, right, would be 2 by 2 equals to 1 by 0.46. So, SiO2 is nothing but it has a compressive stress. Now, this kind of thing we need to understand when we fabricate a micro cantilever, right, because we have to compensate the stress created by silicon dioxide by using another film which can be silicon nitride. So, you can see here very clearly silicon wafer, right, and how the final thickness we can obtain from silicon dioxide, right, depending on the molar volume of the silicon, depending on the molar volume of silicon dioxide. Molar volume is nothing but molecular weight by density. Same thing, the molecular weight of silicon is 28.9 grams per mole, density is about 2.33 grams per centimeter cube, while we take about silicon dioxide, it will be 60.08 grams per mole by 2.21 grams per centimeter cube. That is why we get this 0.46 factor, and we can use this 0.46 factor to understand what is the compressive stress created by the silicon dioxide film that we are growing using either dry oxidation or we are using the wet oxidation technique, right. So, in the next module we will be learning the techniques to grow silicon dioxide. What we have learned until now? We have learned until now is how to get a silicon wafer from the from the bowl, and also from the ingot or ingot, from the ingot, and how to create the silicon wafer from polysilicon to silicon. That is what one thing we understood. Second thing we understood is that substrate can be of different type, can be silicon, glass or plastic. third thing we understood is how can we grow silicon dioxide on silicon wafer. So, the growing techniques we will understand, but what are the use of silicon dioxide if we grow on silicon wafer. Right. So, in the next module let us see what are the techniques to grow silicon dioxide. We have seen dry oxidation and wet oxidation, but how the equipment will look like, alright, that we will see in the next module, followed by what are the characterization technique, how you know what is the thickness of the silicon dioxide. Alright. So, till then you learn this class and learn this lecture, and I will see you in the next module. Bye.